Welcome to Earth Systems Lab 2026. It is official. We are kicking off the 11th cycle this year. So incredibly excited to see what this holds. We have three challenges from the Earth Systems Lab perspective. So this is in very close, deep collaboration with ESA, PhilLab, and the team there. So the point of today is really just to get the ball rolling, get the excitement up. I'll start with a very brief introduction to Frontier Development Lab and Earth Systems Lab for those of you who might have been slightly lost and wandered in and never heard of this before. But most of you would be very, very familiar with Earth Systems Lab and FTL in general. Then we'll jump into what everyone's been waiting for, the Earth Systems Lab 2026 challenges. A very brief overview, but then more to the point, some challenge-specific insights. Ooh, got the nice reverb going there as well. Yeah, challenge-specific insights from the FTL teams who will be driving this. And then I would love to get a lot of conversation going throughout this call. So for each one of those challenges, we'll pause for Q&A. And throughout, please do make use of the chat functionality to share any thoughts and the questions as we go along. After going through the different challenges, we'll round off with what to expect, what's coming next. And then we'll also give an opportunity for programmatic questions and answers right at the end of the call. So without any further ado, just want to remind folks who may be new to the FTL community and dialing in for the first time today that there's a fantastic amount of information on ESL Lab or eslab.ai. So this is the Earth Systems Lab website, including the results from last year. So incredibly proud of the teams from last year. Had a clean sweep at Europe's, also a Best ML Innovation Award at the Climate Change AI, but absolutely fantastic outputs across the board. So please do take a moment and be sure to review some of those outputs, not just from last year, but from previous years. The other catch here is that we are still accepting applications. We haven't publicized that too loudly. Application deadline has come and passed, but officially will be closing down this weekend. So QR code right over here on the screen, or if you want to, here is the actual website to apply. So friends, colleagues, family, if so, please do let them know, because that is a very hard deadline for applications. So just a very quick introduction to FTL. FTL is a more general set of programs. We here today with Earth Systems Lab, which is very much focused, as you can imagine, on Earth systems, Earth observation, everything climate resilience, crisis response, and such. But what makes FTL special is that we don't just approach these things in a general theoretical sense or a siloed sense either. It's all about interdisciplinary research. It's about bringing the best of academia and industry together and moving forward incredibly rapidly for applied AI outcomes. So we've had a fantastic legacy with our sponsors such as NVIDIA and Google, and one can really see the two-way flow of knowledge and expertise, both from industry best practices influencing how we do things, and similarly FTL showing Google and NVIDIA sometimes how we could do things. So for the last 11 years, we've been focusing on using AI for applied outcomes, looking everything from the sun, how the sun affects us, our dynamic planets. That's now Earth Systems Lab, and most recently last year also officially with Lunar Lab, looking at the moon and our solar system. And as I've said, it's really about defining the sort of the applied use cases where we want to be protecting our environments, our infrastructure, our communities. So yeah, always thinking about that. Over the last 11 years, a huge amount of fantastic outputs. So please do take some time and look at some of these outputs. I will mention some because this year we do have a couple of challenges that are following in the footsteps of previous FTL outcomes. So that's always fantastic to see the kind of full circle where foundations are built and then one's growing the program on top of that. I just also want to introduce, you will see over the next couple of months, a lot of these faces more and more. This is the European um, team from Trillium Tech, who is going to be facilitating and supporting FTL in general. So you would already have probably got quite a few emails from Carmen and Tom, the amazing team behind the scenes working to make this program a reality. As myself, technical program manager, and also joining us today on the call is the amazing Belina Raffi, who creates all the secret sauce behind this, the collaboration that is needed to sprint. We also have online today Will, who's absolute guru when it comes to anything data or technical, and would be assisting with that. And yeah, with every year it's hugely exciting to see the amazing design assets that come out, and that's all due to the design team. So Anna and John, I'm not sure if they were on this call, but you will see some of their amazing outputs nevertheless. And then of course we have James Parr, director, Jonathan Knowles, exploration director, and Jody Hughes, who are in the background leading this entire FTL initiative. So very briefly, how does FTL work? So I've just introduced the FTL support team. We're really here to help make the magic happen, but it's ultimately the research teams that do that. So we have faculty who are guiding a team of researchers, and within this kind of container that is FTL and Earth Systems Lab, sprinting towards outcomes in a very rapid period of time. But I would like to emphasize that it's we often say it's a sprint, it's always rapid, but that's doesn't diminish the kind of work that gets done, and one sees that with the outputs, seeing publications at very high impact journals and conferences. So it's all about integration and this collective intelligence, bringing all the right ingredients with expertise from different domains together, and working together to achieve these outcomes. We're sitting here now, mid-April. We're very much in the recruitment phase. So even though applications are closing, there have been a fantastic number of candidates already coming through this process, and very excited to see what that matchmaking would look like, getting these candidates involved with the different challenges. FTL is a year-long process as well, so there's a long lead up to this, a lot of discussions with ESA in particular for Earth Systems Lab, and then the kind of preparation that helps us kick things off in just over 2 months' time. So mid-June is when we actually have the research sprint starting. That continues to mid-August, but then there's a kind of a cool-off period, and we see a lot of these outputs being presented at things like NeurIPS towards the end of the year. Also, very briefly, just wanted to give a bit of context where we get these challenges from. It's not just sort of pulled out of thin air. It is very much a process that starts in previous years, largely. So, as noted, some of these challenges you'll hear about today have their seeds in previous years of FTL and are matured. So there has been quite an extensive period of refinement from initial ideas, sort of one pages, which was seen across workshops this last year in a global context, in the US, in South Africa, of all places as well. And each one of these workshops have added some thinking towards what ultimately has become the concept members that have been signed off and now are being refined as we speak. As a kind of a catch-all, what we are looking to achieve with Earth Systems Lab in 2026, it's really looking to develop that nervous system for planet Earth. So we've been doing this for quite a long time. We've been, as line here says focusing on developing planetary intelligence. That's a big catch-all term in this changing world. But I would want to emphasize the last bits where the research portfolio is not just at monitoring kind of perspective, but looking for active stewardship to understand where do some of these outputs actually lead in terms of decision making and what can be done with them. So. Um, I don't want to give too much away because we have some fantastic FTL experts on the call who can jump in and give more context and bring these challenges to life. But just wanted to say that we have three challenges that is looking at using data from across the East fleet. But most recently, we can also start thinking of the foundation model aspects that become more and more useful as a actual mission concept as well and feeding that in. So it's no longer just satellites that give us data. We can see these foundation models as a very clear mission concept that can feed into science outputs. So to highlight some particular missions, well, there's the Sentinel fleet, which would be informing all of the different challenges, then EarthCare in particular for the tropical cyclone dynamics, and biomass very recently for the living forest challenge. And then we have the set of foundation models, which is growing all the time, which would be feeding into the Mo-Earths or mixture of Earths. I realize I've just given away some of the names, but hope that just is a teaser and nothing more. I also wanted to frame this in a different way. So we've been thinking about the challenges and how we're approaching applied AI for science. And seeing it as not just a single siloed output, but as an entire intelligence stack. So starting off with a kind of a ground layer of perceiving, bringing in new data sources for the first time, processing where sometimes you have different data sources that together give you new insights, and then planning where once you do have all of these together, how does this inform decision making? And one can see in a very hand wavy, rough way that each one of these challenges fits one of these levels. So following forest for the first time using biomass data and augmenting it with the other data sources for a downstream use case, in this case, living forest, and processing. Similarly, there's already been some work done on these data sources, but bringing them together with new insights, and then planning, taking into account foundation models for downstream use cases and having an intelligent way of choosing which one is best for your outputs. So yeah, none of these would be seen as siloed. There are huge amounts of overlaps between them, but just another way to frame how we think about these challenges. So without further ado, I would love to hand over to the first of our teams. So we've got, I believe, Kai online. Yes, indeed, and Shruti, who have already started having a look at defining and refining the first challenge, which is mixture of experts, but more aptly mixture of Earths. So with that, I would love to hand over.
Yeah, thanks so much, Mike. I'll share. Okay, Shuli?
Yep,
Okay.
sounds good.
Okay. Um, I tried to come up with a more or less nicely looking slide based on the initial sticker that I had. Unfortunately, I didn't have the triangle yet for the mixture of earths, but I guess for the next time, so now we can include that here in the slides. So yeah, well, I guess Shruti and I had our first discussions on this now in these past days, bit of reading, bit of writing. I'm super excited to be, well, part of this project this year. I mean, as most of you, I guess, know, I was part of the team last year as a researcher, and I'm happy that this project basically picks up a bit the work of what we've been doing last year. I don't have a clean sleeve yet. I'm still wearing, I guess, my suit from last year with my background. So yeah, let's basically start where basically this project picks up on. So in the last 2 years, I guess, FDL had some sort of preparation for this. In 2024, I have to admit that I have not completely read in detail on how this Maestro was set up, but so on a like on a very simple basically level, what Maestro was doing was basically picking from a suite of different foundation models for a certain task the best suiting one, right? So it would basically, depending on like the different representations that would be produced, and depending on the input, choose which model for the downstream task would be the most suited, and this representation would be sort of waved through, right? Basically, a bit in a similar vein was what we were doing in 2025 with Shrug FM, which we have now also published or accepted at least. Was this project of, okay, how can we get uncertainty quantification into our foundation model? How can we make our foundation model say, I don't know, right? Maybe most of you or some of you have already heard that phrase before. So yeah, in principle, we worked a bit further on our pipeline. I think most of you have seen maybe the first half of the work. Now we've refined it a bit. We've basically now 3 flags on the input now, really on the input signals, then the embeddings, and on the downstream tasks, like wonderful signals that we unified in some selective prediction mechanism. So basically, we've set it up in a way that now the model can, based on different steps of the procedure of the foundation model, give us an idea of why we might be wrong, right? If there's a problem maybe already in the input, if there's a problem maybe related to the foundation model itself and where it maps the input, and then also the downstream task, right? And now the next step, basically based on this, would be, okay, can we now maybe use a whole suite of foundation models and a whole suite of foundation models and basically use these signals that we've basically come up with to kind of find an adaptive mechanism that could get the best of these different models, right? Maybe merge them in some way. So this kind of combines the 2 ideas of Maestro and Shrug FM, but more in an integrative way, instead of just choosing one and then just sticking to it, but rather like fusing maybe in some way. So the idea of the mixture of Earths basically stems from, I mean, Mike already mentioned this, the mixture of experts, right? This is basically an architecture that is being used for large language models, for instance. That's basically where it came from. I think already in 2018, there was a paper that suggested this. And it basically, like, you don't need to understand the full transformer here. There's just this block in here within the transformer that is just very heavy in weights, right? And the mixture of expert basically substitutes this with a lot of smaller ones, like small experts. And there's an internal router that basically chooses which one for your task might be more suited. And this makes the models much slimmer, more efficient, and everything, right? So this was suggested basically to make smaller models so that, as a way to democratize maybe large language models. Now, there are similar structures already that have been applied in this similar vein, like with the architecture for Earth observation, right? There's this mixture of expert, like ring mixture of expert for Earth observation that was, I think it's on right now on archive. I forgot to put the reference here. But basically it does the same thing. You've got internally within your architecture, like these smaller networks, and it basically chooses which one is more suited. Now, this is all trained end to end, right? This is its own basically foundation model that uses this. There's another basically model that has been proposed where basically they use different specialized experts, right? So they do use different encoders that were trained, supervised for different tasks. So they use one model that was trained for flood detection, one for land cover, canopy height, and then also have here like a gating mechanism that chooses which model is now for the task more suited. So this is basically kind of what exists in this way. And I mean, this is also for Earth observation. And now basically the question is, which brings now these different things together, Shrug FM, Maestro, and the idea here of this mixture. Can we build a model that basically uses a mixture of pre-trained foundation models? So instead of these specialized models like they had here before, can we just use a suite of foundation models and also find a way to adaptively bring them together to get the best of them for whatever downstream task you want to tackle, right? And yeah, how to do this and what to tackle, I guess that's the big open question. And with this, I give over to Shruti.
Yes, thank you, Kai. Um, so we didn't necessarily want to be so prescriptive at this initial state of how we plan to tackle it, but in the spirit of FTL, obviously, we want to build on work we've done. And so the idea, and also I think the strength that we propose is, what if we could build from Shrug FM's framework and just simply extend it to the Pangea dataset to understand what Shrug FM is built for understanding, which is failure modes of various GFMs. Um, so use that strength to our advantage, and then sort of go a step further, as Kai said, think about how we can go beyond an ensemble of specialist models to already having generalist models that are meant to have a lot of representation power, which allows us to move from static representation driven mixture of experts to a more dynamic reliability driven switch out mechanism using Shrug FM's framework so that we have a mixture of Earth foundational models. I think, personally speaking, the main strength here is that it lays the runway and moves beyond just simple model building to allowing for modular deployment framework where you can actually deploy and ingest newer FM architectures as they come out. But it's really laying the runway for these things to be used instead of just being built. So yeah, we hope to get some cool spider diagrams like what you see below here, but really just as a first step, see how we can actually test the reliability under stressful situations across a range of GeoFEMs for a great benchmarking data set that already exists. And if we're able to do this correctly, the next slide sort of gives an idea of what the possible test cases could be that we could design then once we've got this switch out mechanism set up. And so we can already, using domain expertise, know what kind of switch out we expect under given scenarios or situations. And so, for example, in situations there is lots of optical noise, maybe there's lots of clouds, for example, we could test whether there is a switch out from a SAR-based to a SAR-based biomass XBART model, so a model that's trained mainly on SAR images. And we could test that, for example, when looking at a mixture of experts for biomass estimation moving from North American temperate to Southeast Asian mangrove forests. So that's one. Another one, obviously, is disaster monitoring. Again, using domain knowledge, we could say, well, we know that for smoke, for example, it's easy to confuse it as a shadow if you're not a shortwave infrared expert. So we could then test whether there is this switch out mechanism for detecting burn scars where it weighs these experts more. So it would be a good way of validating it, but also a good way of testing that we've got a robust runway for future deployment. And that's sort of the idea for now.
Absolutely amazing. Thank you. Thank you both for setting the scene there well, folks, because I would love us to possibly have a few questions in that while folks are getting their thoughts. Just a comment from my side. Can't wait to see what the new hashtag would be there. From hashtag I don't know to hashtag I know someone who does. But with this, and I love the framing there of the kind of the modular aspect and building for the future. There's quite a lot of sort of engineering challenges, and I was wondering if you had any initial thoughts on what's the big scary challenge in that context could look like, and yeah, what would keeps you up at night, or maybe not yet.
Shruti, you want to go? You...
Hi, you go first. I think you have more experience with this, given that
Oh,
you
well,
were
I
more
mean,
so the researcher last year.
yeah, that's a fair question. I mean, I think to me the scariest thing here is really I feel like it's similar-ish, maybe a bit even higher scale than in the previous challenge because there's so many things you can do, like so many signals. Like there's really I feel like it's endless, right? Because like when it comes to like in the previous one with Shrug FM, right? The all the signals like that you could come up with, all the ways you could get uncertainties here and there, and on the end, right? There's so many things you could do, and then the big question is like, which is the one that scales well enough to our problem, right? And I feel like also here, as we're moving from a single foundation model to now a group of foundation models, that sounds also computationally a bit scary. Then on the other hand, of course, there maybe, also the argument here again would be, given that we like similar to the mixture of experts, right? The goal would be to make it sort of more efficient in the sense that you don't need a single gigantic model that can do everything, but you can find a way that you have a bit smaller ones, but that kind of can compensate each other's weaknesses, right? So I guess it's probably part of the task to find suitable models, right? That are not too gigantic so that we're not overdoing it, right? I think for the prototyping, for showcasing that this works, we don't need to go for the biggest of the biggest. I think so this is my hope, right? But it is attached to a fear, yeah, for sure.
Completely.
Yeah, I think that.
Yeah, I was going to say
Go
this
ahead, Shruti.
resonates a lot, and I think, yeah, probably we're going to have to be very careful with which models we pick at the start. I have a couple in mind, so at least we can flesh through those. But I know that also Kai probably knows this better, but the method of downstream uncertainty estimation from the deep ensembling is also quite computationally heavy. So we need to definitely make sure that from the start we're not burning through without reason. Yeah.
Yeah. No, good
Mhm.
problems to have in a way. Um, any other questions possibly from the online folks? Yeah. Awesome. And this is really a great start, and I realize it's very, very fresh. So
Yeah.
looking forward to diving into this deeper and deeper as we get closer to kickoff.
I would also just like again mirror the question from Shruti. Like if any of you thinks like they have a good task for this problem where you think this might be suitable, then please let us know. If you have a nice data set, whatever. We're still very much on the lookout for something there. Also, I mean, especially because we somehow in our proposal biomass ended up in there. And I know there's a specific biomass challenge. So if those folks are down for some symbiosis, let us know. Yep.
We can just chill for 8 weeks and give you the
Absolutely.
project.
I just thought this was a beautiful segue into the next challenge. So, Joppe and Grace, thank you already for jumping in on this, and floor is yours.
All right. Let me quickly. Voila. So some of the people who have been following FDL for a bit know that like in a previous episode of FDL, there's already been a biomass project where we used existing SAR data for biomass applications, but that was of course a precursor to the biomass mission. And Grace, among others, who's in the call here, did some amazing work. I think she, better than anyone else, can touch upon what was actually done in that project.
Thanks, Joppe. Yeah, so this, as Joppe mentioned, this was a precursor to the biomass satellite being launched. So we were working with quite a really small test set of data from aeroplane flyovers. But the whole idea behind this project was to give ESA some insights about the potential benefit from the biomass mission. So a higher number of SAR images were captured. And we also looked at inputting different forms of SAR data and different points along the processing pipeline. I won't go into it in too much detail, but there's quite a lot of like radiometric processing that SAR data needs. So we were testing whether we could skip that stage and still get a good estimate of the biomass and the tree classification. So that was the work that was done 2 years ago. And I think my understanding is that ESA are keen to collaborate again on biomass.
Amazing work. And as you all know, they grow up so quickly. What was built for a as a precursor to biomass mission is now actually up in there, measuring our forests, making beautiful images as we speak. So there must be amazing things you can do with this data. So that's what we're going to try to do. But of course, a forest is more than my no, I thought my headphones fell out. Um, there's more than just the biomass of a forest to know how a forest is doing. Some of the people who were around 2 years ago might recognize this one. I don't know if my sound is actually being shared.
Nice.
So what you would hear if my sound would be shared is the sap flow inside of a tree. So a tree is more than just a bunch of biomass. It's alive. There's things happening in there, and you probably also the famous Keeling curve, you can also see in there what they first thought was like an anomaly in CO2 data, is that you really see the seasonality in what happens in trees. Data that's easily visible from other satellite products. Here, for example, you see like leaf area index really evolving over the seasons. You can really see that's forests in more than just a bunch of wood that's just there. And we want to experiment with what we can do with combining this more static data that is biomass, this interesting data from biomass mission with more dynamic data that could maybe be an indicator of stress in the trees. Think of temperature, think of how much it evaporates. And there's some interesting developments in machine learning that we want to work with. For example, some of you may have heard about JEPA, Joint Embedding Prediction Architectures, is that you more and more in latent space that you build world models. So you instead of dealing with all the noise of the satellites, you do everything in the latent space. And that comes with maybe some interesting applications. Maybe we could have like an encoder which has like the latent health of our tree embedded in it. And you do operations to find like the future state of the biomass. That could be an interesting application. Could we maybe perhaps use something like this, such a latent model of our forest to detect stress before we see it, and then policymakers can take the necessary measurements to deal with that? Or could we simulate the impact of certain events on this biomass? What if we know, for example, what the embedding of a forest would look like if you would build a road right through it? That will probably have impact on more than just those trees that got cleared, but the whole part of the forests. Can we simulate something like that? Either way, I think the part that I'm really excited about in this project is using this rich amount of data, on the one hand, biomass, but also the other Sentinel missions, for example, to combine this static and living part of our forests to really track the resilience of our forests.
Oh,
Any questions
thank you,
about
Big
this?
Grace. Yeah, no, this was absolutely amazing, and yeah, I love the framing there of like grow up so quickly, and no one's unleashing the full potential on what is actually the mission flying. So, yeah, very cool. Let's see, Lena, great question there, just in the chat. Thoughts on how this may be used on the ground to affect change? So in the sense of some of those downstream use cases you were talking about, Jope, how would you see this outputs actually being used?
Yeah, I'm assuming Belina probably means really towards the policymakers immediately. Then if you could have something like this that is very well at like modeling this forest state, then you could say like here's what the impact on this forest would be and our carbon stocks, because that's also related to the European Green Deal, for example, and our carbon stocks. What if you will do this, then this will have this impact. But maybe also the other way around. If we do this part of nature restoration here, could we have an indication on how that will impact carbon stocks? I think there's a lot of interesting ideas that we're also going to be exploring with researchers on what would be downstream use cases in forest resilience and carbon stocks with this biomass data.
Amazing. And maybe a similar kind of question to what I asked before. There's a huge amount of different data sources. That's what one was hoping to tap into. In that sense, are there any that's particularly excite you? I mean, obviously biomass itself, but with that, I guess the challenges with yeah. Um, uh, RFI, and that's just as a function of the sensor itself. So, any particular challenges that you kind of excited about in that sense?
Unlike the data from biomass, or in general, all the data?
General data, but possibly also from biomass itself. Yeah.
Yeah, well, I think either way, I'm pretty excited as well to really start talking to these experts in forest to know what is actually there, because I have myself not worked with the biomass data yet. I also the level 2 data is not available yet there, so that will be a challenge to see, okay, can we do actually something with this more raw biomass data? Could we maybe try to already get some level 2 data on the, yeah, actually above ground biomass products? That's also something I'm excited to see if that would be possible by then. Because yeah, it's of course it's SAR data. It's more challenging than what's more intuitive and optical. But yeah, I'm excited to see what's possible in there, and combining that with other living data. Like in my lab, they're very specialized in evapotranspiration, which is really strong signal of the health of a tree.
Makes two of us. There are a few questions in the chat, and maybe if I can ask just to answer there, because we have one um, remaining challenge here, and let me jump in and present. So we have a challenge which is coming from uh, a previous set of challenges as well, and we'd love to welcome Anna and Emiliano to share a bit about what is now tropical cyclone dynamics.
Okay, so the challenge that this is about will be about tropical cyclone dynamics. So a little bit about the motivation, why tropical cyclones. So just to take it from to start with an example, Dorian. Here we see a snapshot of Dorian based on geostationary image on the left, and then on the right, some of the destruction that it caused. And so in this case, for this example, which happened in late August 2019 in the Bahamas, the Dorian tropical cyclone, the storm rapidly intensified to a Category 5 storm and caused widespread destruction, as you can see, and the loss of 200 lives. So basically, we want to really take on the challenge of early warning systems and help to give a heads up so that people can properly prepare and protect lives, basically. So this is kind of the motivation for this challenge. So this is a problem that's not really solved right now. There's pretty good machine learning based models or hybrid physical and machine learning based models for predicting the track of a tropical cyclone, but not really for predicting its uncertainty, its intensity, right? The kind of the intensity of the winds of the tropical cyclone. So this is what we really kind of want to tackle. And two of the reasons, perhaps, that the current models don't properly or don't perform very well at this task is that they don't, on the one hand, they don't properly represent the 3D microphysical properties of the tropical cyclone. And this has been shown, or there is some evidence that this is key to a key causal factor for the evolution of a tropical cyclone's intensity. And then on the other hand, another thing is the resolution of that the models work with, the forecasting models work with. They're often 1 kilometer to 10 kilometer resolution. And at this resolution, you can't properly resolve certain aspects of the tropical cyclone, such as the eye wall, which are key factors in order to be able to predict its intensity going forward. So basically, this is kind of our starting point. These two opportunities in tropical cyclone modeling at the current moment. We're also building on last year's project, actually 2 years before. So during 2024, there was a challenge that was to build 3D reflectivity maps of clouds based on 2D geostationary satellite imagery. And then last year we kind of picked it up again and tried to make it more specific for tropical cyclones. So the way that we did this for 2024, we were only looking at Europe using the MSG geostationary satellite. And so for 2025, we made a much more global data set, which was more adequate for observing tropical cyclones. So we included 3 geostationary satellites, MSG for Europe, GOES for the Americas, and then for Asia and Oceania, we took Himawari, and we built a data set and some models that were able to look at tropical cyclones in 3D, and also specifically we modeled also cloud microphysical properties in order to be able to get closer to actually forecasting tropical cyclones. So we made some huge steps towards being able to observe in real time tropical cyclones in its 3D structure, which, as I've mentioned, is so important in order to be able to forecast their intensity. But we weren't able to do some of like the time series modeling. We just basically looked at snapshots of the geostationary satellite, and with these snapshots predicted the 3D structure, but we didn't model the dynamics. We didn't really look at a time series types modeling where you look at several time snapshots and model the dynamics of what's going on in the tropical cyclone. So this is basically what this challenge is about. And just to show off a little bit of what we achieved last year, this is kind of what we were able to model, based on a snapshot of a geostationary snapshot of a tropical cyclone. We can build a 3D map of reflectivity, which is what you can see in the gray scales. And then also in the blue scales, you can see the 3D structure of a microphysical property, in this case, ice water content. So now we want to see, okay, can we use this 3D maps of the clouds of the tropical cyclone, plus some additional information, in this case, mainly focusing on very well-resolved SAR-based surface wind fields. And then, so can we fuse these two types of information that give you the 3D, but at kilometer scale, kind of horizontal kilometer scale pixels, let's say, and then much more well-resolved 10 to 20 meters SAR-based wind fields. And can we fuse this information and come up with a new generation of machine learning tropical cyclone intensity forecasting models, which include this very key input informations that current models don't take into account. And so a little bit of the idea, just to visualize it a little bit, as we are going through observing at different time points, some of the challenges for this modeling will be that at different time points during the evolution of the tropical cyclone, we might have different sources of information. So here, for example, in the first, we might have geostationary, we might have some vertical profiles, radar-based vertical profiles, SAR-based wind fields based on the lower the surface, so the lower part of the tropical cyclone, and then we have the geostationary look, which looks at the upper part of the tropical cyclone. But then at a different time point, we might only have geostationary and vertical profiles, and then at another time point, we might only have the SAR-based wind fields, right? So these are some of like the tasks that we can attack during this challenge. How to combine upper layer and lower layer information. How to combine different input modes that are available at different time points, from 3D microphysical, SAR-derived wind fields, era 5 reanalysis data, or other modes of information that we might choose to work with, different resolutions of input information, and spatiotemporal machine learning models that take into account the dynamics of the tropical cyclone. So yeah, this is basically what excites me most about this challenge is, how can we use all the different lessons from deep learning in recent years, foundation models, working with different, fusing different modes of information on the one hand, so kind of these deep learning super large models based on lots and lots of images. And then at the same time, how can we use more sparse models such as spatiotemporal graph models that don't have that large amount of information? So for example, for tropical cyclones, we might have in the order of hundreds of tropical cyclones to work with, of course, with a lot of density so for each one, we might have lots of observations at different time points, but different tropical cyclones, we might only have in the order of hundreds of different ones. So we're kind of mixing, deep learning for looking at lots of different images, but more sparse graph-based deep learning for the kind of sparser scale of when you're looking at the scale of one hurricane and its evolution, right? So this is something that's quite exciting to me. I'm also very excited about answering some of the questions. For example, we've derived some 3D microphysical properties. Are these actually useful for modeling proper downstream tasks, such as modeling the dynamics of a tropical cyclone, and actually looking at maybe what is the different value of each of the different sources of information at different time points of the tropical cyclone evolution, and how does having one or the other types of information, how does this affect the forecast skill of machine learning based forecasting models. I guess I should mention also, for now, the goal is to produce machine learning based forecasting sub-kilometer models for the surface wind fields at a 6 to 24 hour lead time, which would allow a decent amount of time for early warning systems to be able to be effective for these tropical cyclones. That's all we have, I think. And if anybody has any questions.
Yeah, no, amazing. Thank you, Mediana and Anna, for putting this together. Very exciting to see the kind of that next step and the predictive sort of aspect here. In my mind, just you talking through those different scales and like temporal and spatial, and putting them all together, real cutting edge stuff. And I know we say that this is a challenge that's building on a lot of previous work, but I feel like that might be slightly misleading because there's a lot of very meaty bits to get into here. So fantastic. Any questions from folks online?
I had a question, if you can
Yeah,
hear me.
Alex, please. Yeah, please go ahead.
I was curious on, I mean, there's such a large amount of data to do something like this. So how is the annotation done? I might have missed the part that was like, how's the data being labeled today for your data set, or is it already labeled ahead of time, or is this something that you guys are kind of doing, by hand or automating at some point?
So for the this I mean it's an important question because for wind fields we're working that out right now, but at least for everything else, there are some data sets that match all of these different satellites together. So for instance, there's a data set called TC Primed, which is specifically for tropical cyclones and tries to match whatever available satellite overpasses you have. So something like that we can leverage. But from the previous years, there's a lot of data engineering at the beginning to do all of the temporal and spatial matching ourselves. So we're going to try to see if we can reuse as much of our previously created data sets and leverage data sets that already exist, but we're probably not going to get around creating some type of new matched up data sets to make sure that we have all of the satellites that we care about and all of the annotations that we care about as well. Because of course they're, ordinarily provided separately.
There are already some data sets that have, like, for the tropical cyclone track, the wind speeds. So there is some sort of already available data sets that has, certain points in the tropical cyclone track and the respective intensity of the winds. So as far as just the target, the machine learning target, I think that would already be available. I don't know, Anna, if you remember what kind of wind speed, like, is that a measurement, or is that reanalysis data from those data sets, or is that?
So I'm guessing it would have been derived through similar ways using synthetic aperture radar. So then whatever original satellite data it comes from, you have the problem that you also have specific overpasses that would provide that information. Maybe it's SAR and additional observations that provide this. But so then, as Emiliano has said, like the annotations might exist. They might have been paired already with some data sets. If those are all of the data sets that we're going to end up needing is another question. So we'll have to see, but the data exists somewhere. But maybe it's not, on the same grid and the same time periods. So we'll see. But in an ideal world, we'll try to keep data engineering to a minimum, as we always say for every project, and focus more on the modeling, but we'll see. But yeah, the thing that really excites me about this is that building on our previous work, we're using the 3D cloud products not as an outcome, but as an input to the data. So we're sort of treating this a little bit as done, and using it more as a scaffolding to see what interesting science we can get out of this next, which I think is a nice graduation of these projects into something different rather than, sort of touching again on the same ideas.
No,
Thank you.
absolutely.
That provides an answer that's great feedback.
Thanks. Okay, we're getting close to time, folks. So I see here's a question in the chat just from Abdullah. I wonder if we can take that on chat. I'll very briefly wrap us up and get us all home on time. So to that last point, just where things are at, all these challenges, as you've heard, are really pushing the envelope. They're brand new and seeing what can be done. Possibly clouds are slightly ahead of the other challenges. So in the TRL scale, as we often look at it from an ML perspective, we're dealing from a low to mid TRL. So this is ultimately where we want to go. And really, as you put it there, Anna, great to see the kind of graduation of some of these outputs, not just being the next version, but actually inputs into new science. for folks just to see the timeline coming up, we're sitting right here mid-April. Applications, as I say, close officially end of this week. So please do, if there's anyone you know that is sort of sitting on the application, please get it in. We have a 2-month period until kickoff, so literally 2 months away, 15th of June, and the sprint running through to the 7th of August. So across this, we will be having our regular reviews, formal reviews and informal reviews, and after the live showcase, a period of maturation, which ends in the technical showcase in October. Just also want to say it's going to be fantastic to return to Frascati, just outside of Rome, being hosted again by Isa Isrin, and this year at Villa Toscolana. So very, very excited to have that first kickoff week in person. A little bit of an outlook for that. So we have for Earth Systems Lab a in-person week right at the start of the sprint period, when we then transition into a virtual context. So as I say, hosted with ESA, and then also a few days of group work that really gets the ball rolling for our first deliverable, which are the big Y presentations. So if some of these intrigue you and you would love to hear more, the first output of the FDL System Lab 2026 sprint will be this 19th of June, a big Y presentation, and always a great to see where the teams are going for this year. As I mentioned, the sprint itself will have the opportunity for a number of different inputs through the FTL formal Friday. There are 3 reviews, so we'll keep everyone in touch with regards to those dates, and one can be tracking the progress as the teams progress. So these are all virtual. Finally, really looking forward to having the community get together again. Community is that thing of last year's outputs. So with that, thank you very much.